Bonus, section 29.7, concepts and calculations. So example 8, sunlight and the photoelectric effect. So this is just getting an extra example in there, which is pretty great. It says sunlight whose visible wavelengths range from 380 to 750 nanometers is incident on a sodium surface. The work function for sodium is 2.28 electron volts. Find the maximum kinetic energy in joules of the photoelectrons emitted from the surface and the range of wavelengths that will cause photoelectrons to be emitted. So this is going back to our photoelectric effect, right? Where we know that there is some sodium surface and we have some incoming light. And if it's of enough energy, then we'll get a photoelectron to be emitted from the surface. So let's, figure this out. So we know the work function, they specified that for us. Work function WO for the sodium is this 2.28 electron volts. Oops. There we go. And then they also give the range of visible wavelengths. So 380 nanometers up to 750 nanometers. All right, and then keeping in mind what we want to find the maximum kinetic energy from these visible wavelengths. And we also want to find the range of wavelengths that will cause photoelectrons to be emitted. All right, so that's a good note to have up there. I'm going to stop the share so we can see it a little more clearly. So here's our picture. And we know if we're talking about photoelectric effect that we automatically have that our kinetic energy max is going to be equal to HF, the energy of the incoming light, minus the work function. So this is a really handy equation. Another one that's really useful to us is this is the energy in terms of frequency, but we also know that the energy can be calculated in terms of wavelength with hc over lambda, where lambda is the wavelength. All right, and on the slide, there was an optional tool that was mentioned. This is one that I'm going to use here. The book doesn't use it, so you don't have to use it, but that's that hc, this quantity on the top here, is equal to 1240.0, so very precise, electron volt nanometers. So very specific units, but has a very specific result that we'll be able to see. All right, so instead of HF, I'm going to want to use this HC over lambda. And this is already set up to solve for KE max, so that's great. So HC over lambda minus the work function. So if I want to get the maximum kinetic energy, as I'm paying attention to the range of wavelengths that are possible to get the largest amount of energy out, to get the largest kinetic energy, since wavelength is in the denominator, I want to have the smallest wavelength. The smallest wavelength will produce the largest energy. So I'm going to use my 380 nanometers here. And here I'm going to highlight why the 1240 can be useful. So I'm going to plug in 1240.0 electron volt nanometers. And now I can plug in my 380 in terms of nanometers, because that's the units above. I'm also going to leave my work function in electron volts because that's the other unit that appears in this 1240 term. So minus 2.28 electron volt. So we notice the nanometers will cancel properly. And now we have a relatively simple calculation. Instead of having to multiply Planck's constant, which is tiny, and the speed of light, which is fairly big, we just have 1240 divided by 380. That comes out to 3.26. If I minus my 2.28, then I get 0.983. and that is in electron volts. Now, if the problem doesn't specify, you can present your result in electron volts, and that will be totally valid. This problem, though, does ask for it in joules, so we're going to need to do the conversion factor. And that's that in 1 electron volt, there's basically the charge of the electron, 1.6 times 10 to the negative 19 joules. So we'll take our result and multiply by that. We get 1.57 times 10 to the negative 19, which I believe does check out. Let's double check. Yeah. Potentially some rounding differences there. So there we have it. We didn't have to switch to joules until the very end, which I find easier to do. Now we want to know the range of wavelengths that will produce this emission of photoelectrons. So we've already found that 380 works. So that one, cool. But will 750? That's going to be the least energetic. It might not. The way we can solve this, rather than trying to plug that in, finding it doesn't work, and then saying, okay, now what, is we can turn around this equation to solve for wavelength, right? Noting that we're going to use the very minimum kinetic energy possible to get the minimum amount of energy needed to eject an electron. So I can angle that down. Let's see if I can do this properly. It's looking all right. So I'm going to set Ke max equal to 0. And now we'll just have that Hc of the lambda is equal work function by solving that equation. So I can now solve for wavelength by swapping it with the work function. So I'd get that wavelength is equal to Hc divided by the work function W naught. And this is something I can, again, plug in my 1240, and it makes my life a lot easier. So 1240 electron volt nanometers divided by my electron volts of 2.28. And now, once again, this is a pretty simple calculation. So let's see. 1240 divided by 2.28 comes out to 544. I don't want to get too low, so I'll move up just a touch. And the electron volts have canceled out, so all we're left with is the nanometers, which is a standard unit for the wavelength of visible light. So now we know it's between 544 nanometers and 380 nanometers, the result we got up above. We can confirm this, show this, if we go back to the slides. There we have it. And so yes, they got 1.58 as opposed to 1.57 times 10 to the negative 19 joules. Notice they converted to joules ahead of time, so they did not use the same, quite the same approach as we did, but they got the same result of the range of wavelengths from 380 to 545 nanometers. So there's an example. One more bonus example that I'll just talk through at least a little bit is the de Broglie wavelength. An electron and proton have the same kinetic energy and are moving at speeds much less than the speed of light. Determine the ratio of the de Broglie wavelength of the electron to that of the proton. So they tell us its speed's much less than the speed of light. We don't know how fast, but we do know we don't need to consider relativity, which is great. And all that we know is it's an electron and a proton, which means we know the mass and the charge of each of them. So what can we do here? Well, the key is that they have the same kinetic energy. Kinetic energy in our classical form is 1/2 mv squared, which we could solve for the velocity, and that's then the square root of 2 divided by m times the kinetic energy. If we talk about the de Broglie wavelengths, we're going to care about their linear momentum, which is calculated with mass times velocity. So then we substitute in that velocity so that it's now in terms of the kinetic energy in the mass, which is much more useful to us because we know the mass and we know the kinetic energy is the same. So that can tell us that our linear momentum is the square root of 2 times the mass times the kinetic energy, using the fact that we have mass times the square root of 1 over mass. That will give us that's mass to the 1/2, or the square root of mass. So using this for our linear momentum, if we plug that into our de Broglie wavelength equation of h over the momentum, then when we calculate the ratio of the wavelength for the electron versus the proton, we find that most things cancel. Planck's constant cancels, the square root of 2 cancels, the square root of the kinetic energy cancels, because we know that the kinetic energy is the same for both. And all that we're left with is the ratio of the square root of the mass of the proton to the mass of the electron, which is flipped because the mass was in the denominator of the wavelength. And so we find that the ratio comes out to 42.8. So that tells us that the wavelength for the electron is greater than that of the proton. So this was a super quick zoom through, but hopefully it highlighted some ideas that might help you as you approach the homework for chapter 29, because that is all the content for chapter 29.